Welcome to a brand new deep dive. Today, you and I are jumping into this incredibly comprehensive 2026 medical review.
Yeah, it's a fantastic paper from the Journal of Clinical Medicine.
Right, authored by Lutomsky and colleagues. And our mission today is to solve this, well, this genuinely terrifying medical mystery.
It really is a mystery.
I mean, why is it that fixing a failing heart doesn't always fix a failing body? Because, usually when we think about heart failure, we rely entirely on this plumbing metaphor.
Right, the pump is broken.
Exactly. The pump breaks, the pressure drops, the pipes back up, and the whole biological system just starts to fail. So the logical solution seems super obvious, right?
You replace the pump.
Yeah. You put in a mechanical assist device or, better yet, a brand new transplanted donor heart, and suddenly the water's flowing perfectly again. Problem solved.
It definitely feels like it should be that binary, like bad pump equals sick patient, new pump equals healthy patient. And historically, the clinical expectation was exactly that. Once we restored that central cardiac output, the patient would just, bounce back.
Hop on a treadmill and go back to normal life.
Exactly.
Yeah.
But then you look at the actual clinical outcomes for these transplant patients, and that entire plumbing metaphor just, well, it completely shatters.
It really does. We are looking at a medical reality that is genuinely baffling. You have a patient who just received a pristine new heart.
Right.
Their central cardiac output is flawless on the monitors. The plumbing is ostensibly fixed. And yet their physical health, their actual capacity to move and exercise remains incredibly compromised.
They're just exhausted.
Yeah, their muscles just refuse to cooperate.
It's a massive clinical paradox, and it challenges a lot of the foundational assumptions we had about cardiovascular recovery.
Yeah, for sure.
What the Lutomsky review does so brilliantly is synthesize data across hemodynamics, immunology, and metabolism to explain this exact disconnect.
Okay, let's unpack this. Because to really grasp why a perfect new engine doesn't make the car drive, we have to look at what the body endured right before the transplant.
Right, the waiting period.
Yeah, and that means talking about left ventricular assist devices. Or, LVADs.
Right, so for a patient in the end stages of heart failure, an LVAD is a literal lifesaver. I mean, it is a mechanical pump surgically implanted into the chest.
Wow.
Yeah, and it completely takes over the work of the failing left ventricle. It acts as a vital bridge, keeping the patient's blood circulating for months, sometimes even years.
Just waiting for a matching donor heart to finally become available.
Exactly. But there's a huge physiological catch with modern LVADs. They are what the medical community calls continuous flow devices.
Okay, right. So think about your own heart right now, listener. A normal, healthy heart operates on a rhythmic drum beat. Lub-dub, lub-dub.
What's a cyclical?
Right, there's a distinct pulse, this massive push of pressure, followed by a momentary pause. But a continuous flow LVAD is, well, it's not a drum. It is a turbine.
It really is.
It operates more like a garden hose turned on full blast, right? Delivering this constant, unyielding, flatline stream of blood.
That garden hose visual is spot on. And that continuous flow, it completely revolutionizes the environment inside the circulatory system.
I can't even imagine.
The entire vascular network literally has to adapt to living without a pulse.
Which is wild. If you live without a pulse for 2 years, how do the blood vessels even know what to do?
What's fascinating here is what happens at the microscopic level inside those vessels. You see, our blood vessels aren't just inert copper pipes.
Right.
The interior wall of every blood vessel is lined with a highly active single-cell layer called the endothelium. And those endothelial cells rely entirely on a biological process called mechanotransduction.
Mechanotransduction. Okay, breaking that down, it sounds like the cells are physically feeling and translating the mechanical forces of the blood flowing past them.
Precisely. Under normal physiological conditions, the rhythmic pounding of your pulse creates a repetitive friction against the vessel walls. We call that shear stress. The endothelial cells are physically stretched and released with every single heartbeat.
Oh, wow.
Yeah, they sense that rhythmic friction, and in response, they synthesize a crucial molecule called nitric oxide.
Ah, nitric oxide.
Right, which is the chemical signal that tells the blood vessel to relax, dilate, and efficiently regulate microcirculation. That's what drives oxygen deep into your skeletal muscles.
So, wait, if I'm understanding this, the pulse isn't just some byproduct of the heart beating?
Not at all.
The pulse is literally the mechanical communication system that tells your blood vessels how to behave.
Exactly. The mechanical force triggers the chemical response. Now, consider the LVAD patient. You take away the pulse.
Oh, right, because of the garden hose effect?
Yeah. You replace that rhythmic shear stress with a flatline continuous hum, so the natural mechanotransduction is instantly obliterated.
Wow. So the endothelial cells just stop feeling that rhythmic
Right,
stress.
their nitric oxide production plummets, and the body just assumes the vessels no longer need to be pliable.
Well, if the vessels don't need to be pliable, what does the body actually do to them? Do they just, like, atrophy?
They structurally remodel. Because the nitric oxide levels drop, the biochemical environment changes, and the body starts laying down collagen and fibrotic tissue inside the vessel walls.
They turn to scar tissue, basically.
Essentially, yeah, the microvessels physically stiffen, they become rigid, they're way less responsive, and the actual density of the capillary networks feeding the skeletal muscles significantly decreases.
Which brings us to, honestly, the craziest part of this entire review. The researchers call this hemodynamic memory.
It's an incredible concept.
It completely blew my mind because it implies that these structural changes don't just magically disappear the second you drop a new beating heart into the patient's chest.
They don't disappear at all. The tissues literally remember the flatline.
That is so wild.
Right, when a successful heart transplant occurs, and that normal drumbeat is finally restored, you might expect the peripheral tissues to just snap back to normal.
Because the plumbing is fixed.
Right, but they've spent months or years structurally remodeling themselves with all that stiff collagen.
Wow.
That persistent hemodynamic memory explains the paradox perfectly. The central cardiac output from the new heart is pristine, but the microcirculation out of the limbs and muscles remains incredibly rigid and impaired.
It's like putting a high-performance Ferrari engine into a car that still has flat, hardened tires. I mean, the engine is revving, but the power just can't actually translate to the road.
That is a phenomenal analogy.
Yeah.
And because that peripheral circulation is still impaired, it creates this huge cascade of systemic issues.
Because it fundamentally alters how the patient's body tries to rebuild itself post-surgery, right?
Exactly.
Right, because if the microvessels are stiff, the skeletal muscles still aren't getting the oxygen and nutrients they need, even with a great new heart.
Yeah, they're still starving on a cellular level.
And this leads to a massive, often dangerous shift in the patient's body composition. Now, I have to play devil's advocate here for a second.
Go for it.
Because looking at the timeline of heart failure, this part initially confused me. Patients with advanced heart failure usually present with something called cardiac cachexia, right?
Yes, very frequently.
It's this severe, involuntary, whole-body wasting away. They lose immense amounts of muscle and fat because their failing heart literally can't supply enough oxygen for basic cellular metabolism.
They are starving from the inside out.
Right. So if an LVAD or a new heart finally stops that starvation and the patient starts gaining weight and putting some meat back on their bones, isn't that a massive victory?
On the surface, absolutely. I mean, reversing a terminal starvation state is always a clinical victory.
Right. You want them to gain weight.
But the tragedy, as this review outlines, is that because of the impaired microcirculation and that hemodynamic memory, the tissue environment is still totally hostile.
Oh, I see.
The weight gain happens, but it is entirely the wrong kind of weight. The data shows a terrifying post-transplant shift.
The fat gain drastically outpaces the muscle recovery.
Almost entirely.
So they aren't rebuilding the biceps and quads they lost during the heart failure. They are just packing on visceral fat around their organs.
Correct. The body essentially swings on a pendulum from cardiac cachexia, which is extreme pathological wasting, all the way over to a state called sarcopenic obesity.
And just for clarity for you listening, sarcopenia is the medical term for a severe pathological loss of muscle mass and functional strength.
Exactly.
Combined with obesity, which in this context specifically means an excess of deep inflammatory visceral fat.
Right. So you end up with a patient who steps on a scale, looks at a standard BMI chart, and seems totally healthy.
Or maybe just slightly overweight.
Yeah. But internally, structurally, they're incredibly fragile.
Biologically fragile. And the Lutomsky paper dives into a mechanism that makes this even more insidious than just, having low muscle mass. They highlight a phenomenon called myosteatosis.
Myosteatosis is a huge factor here.
Yes. Myo being muscle and steatosis being fat infiltration. I was reading this section and realizing this isn't just fat sitting on top of the muscle, like right beneath the skin.
No, not at all.
This is fat actively invading the muscle tissue itself.
It is fat literally infiltrating the skeletal muscle fibers. If you want a visual, think of the marbling in a high-end ribeye steak.
Oh man, exactly. And while heavy marbling might make for a delicious steak, it seems like an absolute biomechanical disaster for a human being trying to walk up a flight of stairs.
It is a complete biomechanical disaster. When fat infiltrates the muscle fibers, it physically disrupts the contractile machinery of the muscle.
Makes sense.
But more importantly, it destroys the tissue metabolically. The intramuscular fat impairs mitochondrial function.
The powerhouses of the cell.
You got it. And it drives severe local insulin resistance. So you have this transplant patient, they have a brilliant new heart, but their muscles are physically marbled with fat.
Highly insulin resistant and completely unable to generate force efficiently. Okay, so let's look at the board here. The patient has a brand new heart, but they are battling hemodynamic memory in their stiffened blood vessels. And they have sarcopenic obesity with these marbled, highly dysfunctional muscles.
It's a tough spot to be in.
Now, if you or I had weak, fatty muscles, the standard logical medical advice would be exercise rehabilitation.
Of course. Get in the gym.
Right. Lift some weights, do some interval training, and force the muscle to rebuild. But the researchers point out a massive, almost unfair roadblock for these patients. Here's where it gets really interesting.
The roadblock is the pharmaceutical reality of transplantation.
Right. The anti-rejection drugs.
Yeah. To ensure the patient's immune system doesn't instantly recognize the donor heart as a foreign object and reject it, they have to be placed on a strict, lifelong regimen of powerful immunosuppressive drugs.
Which makes sense. You have to keep the heart safe.
But what this review brilliantly articulates is that these drugs do a lot more than just quiet the immune system. They act as incredibly potent pharmacological modifiers of exercise adaptation.
Meaning, the drugs are actively sabotaging the biological process of getting fit.
Precisely.
Like you put in the work at the gym, but the drugs intercept the chemical signals before the muscle can actually adapt.
Exactly. If we connect this to the bigger picture, these life-saving, non-negotiable medications are actively fighting the exact biological pathways the body requires to rebuild itself.
It's just so unfair.
Let's examine corticosteroids first, which are, a very common part of this regimen.
Now, when people hear steroids, they immediately picture a bodybuilder getting massively jacked. But corticosteroids, like prednisone, they do the exact opposite of anabolic steroids, don't they?
They do. Corticosteroids are heavily catabolic.
Okay.
They promote muscle protein degradation, meaning they actively signal the body to break down existing muscle tissue.
Wow.
But even worse, they radically alter how the body stores energy, forcing it to accumulate that dangerous visceral fat we just talked about.
But why visceral fat specifically? I mean, why does the drug tell the body to put the fat around the internal organs instead of just, say, under the skin on the arms or legs?
It all comes down to cellular receptor density. The cells in your visceral fat depots have a much higher concentration of glucocorticoid receptors compared to subcutaneous fat.
Oh, interesting.
Evolutionarily, cortisol, which is our natural stress hormone, signals the body to store easily accessible energy around the vital organs during a famine or a crisis.
A survival mechanism.
Exactly. So when we give a patient synthetic corticosteroids, we are hijacking that evolutionary stress pathway and blasting those receptors.
Forcing the visceral fat cells to expand rapidly.
Right, while simultaneously breaking down the muscle to feed them.
It is a completely stacked deck against the patient. But the biology gets even wilder when we look at the other major class of anti-rejection drugs they use, the MTOR inhibitors like sirolimus or everolimus.
The MTOR pathway is arguably one of the most fascinating mechanisms in human biology.
Yeah, MTOR stands for mammalian target of rapamycin, right?
You got it. You can think of MTOR as the master biological switch for cellular growth, proliferation, and protein synthesis.
Okay.
When you go to the gym and lift a heavy weight, you create micro tears and mechanical tension in your muscle fibers. That physical stress activates the MTOR pathway.
Which then signals your cells to synthesize new proteins and rebuild the muscle bigger and stronger.
It is the literal build muscle button.
Yeah, in fact, bodybuilders and longevity biohackers spend thousands of dollars on supplements and protocols trying to optimize and manipulate their MTOR pathways.
Exactly. But in the context of a heart transplant, cellular proliferation is exactly what doctors want to prevent.
Because immune cell proliferation means organ rejection.
Right. So they prescribe MTOR inhibitors.
Which creates an insane physiological paradox. I mean, it's like pressing the gas pedal and the brake pedal to the floor at the exact same time.
That's a perfect way to describe it.
The patient goes to physical therapy, they do their resistance training, they create the mechanical tension, pressing the gas pedal. But the immunosuppressant drug is actively blocking the MTOR pathway, slamming on the biological brakes.
You can do squats until you are blue in the face, but the drug has literally unplugged your body's ability to undergo muscle hypertrophy.
It's the ultimate pharmacological catch-22. And the clinical result of all this interference is that transplant patients develop wildly different exercise responsiveness phenotypes.
Exercise responsiveness phenotypes.
Yeah, breaking that down, it basically means that depending on a patient's exact cocktail of drugs, their genetics, and their hemodynamic memory, their body will respond to the exact same exercise routine in completely different ways.
Precisely. You could have two patients side by side in a rehab clinic, both with pristine new donor hearts doing the exact same structured workout program.
Right.
Patient A might slowly rebuild some functional strength,
Yeah.
but patient B, who perhaps requires a higher dosage of MTOR inhibitors to prevent rejection or is heavily reliant on corticosteroids, might experience absolutely zero muscle growth. In fact, they might just continue to accumulate visceral fat despite working out 5 days a week.
Which completely dismantles the old school idea that we can just throw every transplant patient on a stationary bike, tell them to sweat for 30 minutes, and expect standardized results.
It just doesn't work that way anymore.
If physical movement is being biologically censored by these drugs and fat is just aggressively accumulating around the organs, we have to totally shift how we view human tissue. We have to stop looking at muscle and fat merely as weight or passive baggage on the body.
This raises an important question. If muscle and fat aren't just passive storage lockers for energy, what are they actually doing?
Right.
How are these tissues actively controlling our systemic health?
And this is where the Lutomsky review dives deep into immunometabolism. It's a bulky word, but it simply describes the intense, ongoing crosstalk between our immune system and our metabolic system.
Right. Historically, the medical field viewed adipose tissue fat as an inert biological pantry.
Just excess calories waiting to be burned.
Exactly. And we viewed skeletal muscle as nothing more than a mechanical motor for movement. But contemporary science has completely upended that.
Oh, totally.
We now know that both visceral fat and skeletal muscle are highly active, highly communicative endocrine organs.
Endocrine organs, meaning they don't just sit there, they actively synthesize and secrete hormones and chemical messengers directly into the bloodstream to influence other organs.
Exactly. Let's look at the visceral fat first. That deep belly fat actively secretes a barrage of molecules called adipokines.
Adipokines, right.
And one of the most notorious adipokines it pumps out is called TNF-alpha. TNF-alpha is a potent, aggressive driver of chronic systemic inflammation.
It's bad news.
It promotes insulin resistance, it actively damages the endothelial cells in the blood vessels, and it actually sends chemical signals to the skeletal muscle telling it to break down.
Wait, if visceral fat is pumping out TNF-alpha, that's not just passive storage, that's an active chemical attack on the surrounding tissue. The fat is essentially waging war on the muscle and the vascular system.
It is a literal biological turf war. But the skeletal muscle is not defenseless. It fights back.
How so?
When skeletal muscle forcefully contracts during physical activity, it releases its own army of chemical messengers called myokines.
Myokines, okay.
And one of the most thoroughly studied myokines is interleukin-6, or IL-6. Now, context is everything in human biology.
Right.
When IL-6 is produced by immune cells or fat tissue in a resting state, it can actually act as a pro-inflammatory marker.
That sounds counterintuitive.
It does. But when a massive surge of IL-6 is released specifically by contracting skeletal muscle during exercise, its biological role flips. It becomes profoundly anti-inflammatory.
Oh, wow. It's like the muscle is deploying a chemical fire extinguisher to put out the inflammation caused by the fat.
That's a great way to visualize it. That muscle-derived IL-6 travels through the bloodstream, dramatically improves whole-body insulin sensitivity, inhibits the production of TNF-alpha, and actually signals the visceral fat cells to start oxidizing or burning their lipid stores.
I want to make sure you, listening right now, are really internalizing this, because it completely changes how you should look at your own body. This research proves that your muscle isn't just there to help you carry groceries, and your fat isn't just an evolutionary savings account.
They are engaged in a constant, invisible chemical turf war inside you right now.
Yes. Your visceral fat is deploying adipokines that drive disease and stiffness, while your contracting muscle is deploying myokines that actively heal your vascular system and fight off inflammation. They are dictating your systemic health every minute of the day.
It's a delicate balance. And in the heart transplant patient, because of the legacy of cachexia, the rigid hemodynamic memory in the vessels and the muscle-blocking immunosuppressants, The visceral fat is almost always winning that turf war.
The odds are just completely against the muscle.
Yeah, the inflammatory adipokines are overwhelming the patient's system, driving further endothelial dysfunction and, ironically, eventually threatening the long-term health of the new donor heart itself.
So, if the fat is winning the chemical war and the drugs are blocking the muscle's ability to fight back, how on earth do we rehabilitate these patients? I mean, the traditional gold standard for cardiac rehab is measuring a patient's peak VO2, right?
Yes, peak VO2 has been the gold standard for decades.
Their peak oxygen consumption on a treadmill.
Right. It measures the maximum amount of oxygen your body can utilize during intense exercise.
But based on everything we've just discussed, focusing solely on peak VO2 seems completely inadequate. It's like measuring the exhaust coming out of a car's tailpipe to guess if the engine is fixed, completely ignoring the fact that the transmission is shot and the suspension is collapsed.
That is the exact limitation the authors of the review highlight. Peak VO2 is a blunt instrument.
Yeah.
It tells you the system is inefficient, but it doesn't tell you why. The ultimate conclusion of this research is that modern medicine must abandon the generic one-size-fits-all cardio approach. We need a paradigm shift toward precision rehabilitation.
Precision rehabilitation. What does that actually look like in practice for a patient?
It means designing a rehab protocol that is explicitly tailored to a patient's unique immunometabolic phenotype and their exact pharmaceutical constraints.
Okay, give me an example.
For example, if you have a patient suffering from extreme osteotosis, that heavy fat marbling in the muscle, and they are on high doses of catabolic corticosteroids,
Right, the muscle-wasting drugs.
putting them on a stationary bike for 45 minutes is biologically useless. They might need a highly aggressive focus on heavy resistance training combined with specific targeted amino acid supplementation just to fight off the chemically induced muscle wasting.
Right, you have to fight the specific drug they are on. And conversely, if a patient is heavily reliant on mTOR inhibitors, where their ability to build muscle mass is chemically turned off.
Exactly. For that patient, traditional weightlifting for hypertrophy just won't work because the MTO pathway is blocked.
So what do they do?
Instead, their precision rehab might pivot entirely away from building mass, focusing instead on high-intensity aerobic interval training.
Oh, I see.
The goal wouldn't be bigger muscles. The goal would be increasing mitochondrial density within the existing muscle cells and forcing the stiff blood vessels to produce whatever nitric oxide they still can.
That is so cool.
Precision rehabilitation means looking at the vascular stiffness, the specific fat-to-muscle ratio, the inflammatory adipokine markers, and the pharmacy list, and designing a biological intervention. It is molecular physical therapy.
So what does this all mean? We started this deep dive talking about a broken water pump, but the reality is the human body isn't just plumbing. Recovery after an LVAD or a heart transplant isn't just about restoring central pressure and watching the monitors glow green.
Far from it.
It is a multidimensional, breathtakingly complex immunometabolic process. It involves the physical, structural memory of every blood vessel.
It involves the invisible chemical turf war between your fat and your muscle.
Yeah, and involves navigating the paradoxical side effects of the very drugs keeping you alive. It means we have to view the human body as a deeply interconnected ecosystem. You can't just swap out the engine and expect the old, flattened tires to instantly handle the new speed. You have to actively, precisely rehabilitate the entire biological environment.
And recognizing that interconnected ecosystem brings up a truly fascinating frontier for the future of medicine.
Where is this all heading?
Well, we've established today that our blood vessels hold a physical, fibrotic memory of past flow states. We've established that our muscles act as chemical communication hubs, releasing myokines like IL-6 to fight systemic inflammation.
Right.
And we know that immunosuppressants can lock those muscles out of traditional mechanical growth.
Right. The foot on the gas and the brake at the same time.
So consider this possibility. If the benefits of exercise are ultimately just a downstream series of chemical signals, if it all boils down to mechanotransduction and myokine release, could we one day bypass the need for physical movement entirely?
Wait, really?
Could researchers develop targeted immunometabolic drugs that perfectly mimic the chemical signature of contracting skeletal muscle? For a transplant patient whose muscles are chemically locked by mTOR inhibitors or completely paralyzed by cachexia, could we literally prescribe the systemic anti-inflammatory benefits of grueling workout in a pill?
That is mind-blowing.
Could we force the body to win that biological turf war without the patient ever having to step on a treadmill?
Now that is a profound thought. Replacing the physical friction, the sweat, and the drumbeat of exercise with a perfectly engineered chemical symphony, it really makes you realize that fixing the plumbing is just step one. It's the chemistry of the house that actually keeps you alive, something for you to ponder until the next deep dive.